welcome to the Global Composite Expert webinar series hosted by CDM Hub. This webinar series is to examine the history, present capability, and future of composites, with the goal of sharing the vast knowledge of composites that has been developed over the past several decades. This webinar series is initiated by the leadership of Composite Manufacturing Simulation Center at Purdue University. And we are located in this beautiful building called the Indiana Manufacturing Institute. When life returns to normal, we hope to welcome you to visit us. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. The CDM Hub provides a very powerful website called cdmhub.org for the community to collaborate and carry out this mission together. And we envision CDM Hub to be the premier resource for composite design and manufacturing. And this webinar series is one of the initiatives CDM Hub started as a service to the global composite community. This webinar series are made available by the support of CDM Hub sponsors, including Dassault Systems, Cytec Software Group, MSC Software, through Digimat, Modex 3D. We greatly appreciate their generosity and also contribution to CDM Hub. We invite more organizations to join them and join us to support CDM Hub's mission of convening and serving the global composite community. This webinar will be recorded and made available on CDM Hub, and an email will be sent to all attendees once the recorded video is available. And the presentation will last around 40 to 45 minutes and will have about 15 minutes for questions and answers. All attendees will be muted. Please submit your questions through the Q&A box. Next, I would like to ask Dr. Byron Pipes to introduce our distinguished speaker. Dr. Pipes, please.
Good morning, colleagues. We're delighted to welcome you to this webinar series, and we have a special speaker today, Dr. Ramesh Talreja, who is currently the Tenneco Endowed Professor in the Department of Aerospace Engineering and in Materials Science at Texas A&M University. Prior to this appointment at Texas A&M, we all know that he held the professor position in aerospace engineering at Georgia Institute of Technology. His career, as we know, in composite materials research began at the Technical University of Denmark, where he earned his PhD in solid mechanics in 1974 and Doctor of Technical Sciences, on his collected contributions to damage mechanics in 1985. He is currently a Science and Technology Policy Fellow of the American Association for the Advancement of Science, where he provides, as an outstanding engineer and scientist, his knowledge and skills to address today's most pressing societal challenges. As to composites, his scholarship has focused on the understanding of damage and failure of composite materials with the goal of reliable and cost-effective engineering design. He also serves on the editorial board of the International Journal of Damage Mechanics, and he edited Damage Mechanics of Composite Materials in the Composite Materials series for Elsevier in 1994, and was also editor of Parametric Composites, Volume 2 in Comprehensive Composite Materials, also by Elsevier. We're delighted to have Dr. Talreja join us today and present his lecture on the subject of damage mechanics. Dr. Talreja.
Thank you, Byron. Yeah, I'm really delighted that Professor Byron Pipes took the initiative to put together this particular webinar series, and I'm really honored that he included me in this. I would like to, in this presentation, bring together two developments that have taken place. One, which is sort of more classical, damage mechanics and failure analysis. But the understanding of manufacturing induced defects is something that has taken a different development because of the advances in computational technologies. So simulation is possible today of manufacturing defects that was not possible earlier. So this particular strategy of manufacturing sensitive design that I want to present to you integrates those two aspects, damage and failure analysis and uh, simulation of defects. So these are the topics I would like to cover. I will give you a very brief overview of what's the nature of defects in a manufactured composite product. Then looking at those types of defects, how do we integrate that knowledge and failure analysis into sort of a big picture that I would talk about. And that picture really is the ultimate goal of any engineering, which is to do cost performance trade-off. Then I'll go into certain concepts that are necessary to do this particular type of work. One is the representative volume element. Again, this is not the classical one. The classical one is, I think most of you would know, is for determining average properties. But for failure analysis, one has to do a different type of RVE. And in doing so, one has to make use of certain statistical descriptors that are properly suited to account for the manufacturing induced defects. Then the next step is to conduct so-called virtual testing on the computer. Having RVE is like having a specimen that you go in a laboratory and do testing on, but this particular RVE is the virtual specimen on which you do testing. And at the same time, with computational mechanics, you do failure analysis. So I'll describe those essential steps. I illustrate all of this with two simple examples that are familiar to most people. One is transverse cracking, and the other is failure under axial compression of unidirectional composites. And then I'll conclude. So manufacturing methods are many in polymer matrix composites. Earlier, from the manufacture of boards, glass fiber boards and such, one was doing hand layup, and still in some cases, that is how one does the manufacturing. There are variations of that. Rather than pour the resin, you spray it, or lay up the pre-preg manually in many cases. The automated methods are actually increasing more and more and becoming less and less expensive. And in most cases, they are based on the fiber direction. That is, you have to be taking the fiber orientation as the goal for automated laying off. So filament winding, pre-preg layup, and pultrusion are the common examples of that. Whereas molding methods have developed over the years. The RTM is sort of the classical one. It's variation, vacuum-assisted RTM, resin infusion in various different ways, thermoforming. The main point sort of to recognize here is that any manufacturing method that is controlled well will give fewer manufacturing defects. And as you control the manufacturing more and more, typically the cost goes up. And it's also to do with whether or not particular composite structure allows process control. So with this, I'll show you some images. This is from the Sandia report of 2011, where they went around and looked at actually how wind turbine blades were being manufactured, and took some pictures to show you how things are sort of not as advanced as in the aerospace industry, simply because of the cost. So what you're looking at, this picture to the left is a hand layup of mats in the mold. On the right, you're looking at two parts of the mold that are being closed. And you can imagine that a lot of the labor-intensive input in this reduces the amount of control you can have in producing a quality product. Here are some laboratory examples of intentionally trying to see how defects will come about. So on the top left, you see a case where prepregs were removed too early from the bag in which they were enclosed. So this way, the moisture in the air settled on the surface and diffused itself inside. And then during curing, that moisture expanded to those voids that you see as dark areas. Here you see a void, typically as air pocket trapped between two layers. And then you can see the consequence of that leading to debonding of a fiber from matrix around it. Here you see RTM because it's a low cost typically with much less control. So in some cases you could have a lot of air bubbles left over and they become essentially the undesirable void-like entities and could be causing trouble. Here's again from Sandia report, the section of a wind turbine blade where you can see that thick layers that were stacked on top of each other on curing shrunk and caused a disbond between the layers and therefore delamination under service conditions. Here you see something that has been done in a laboratory environment, but following manufacturing process as it is sort of done in practice. And here are non-crimp fabric layers stacked on top of each other. And after curing, once again, you see the waviness and probably some delamination as well. So I'll come to this particular example a bit later. Joints are, adhesive joints, as you know, are common in composites, and often the thermal expansion mismatch between parts that are being joined together can lead to waviness of fibers close to the interfaces. So you see that's the situation here, and the close-up picture also shows thing here. So this is, say, some airfoil. An example is taken from wind turbine blade. You can see the joints are typically in the leading edge, trailing edge, and between the spar, which in this case is the box girder, and the shell. And so a lot of adhesive joining going on, and control of this particular joint is very difficult to do because what's done is to put a paste-like adhesive between the two parts of the shell. And when you close the shell, the two parts, the adhesive squeezes and takes an irregular shape. Here's a close-up of that. And I think I'll show you a better picture here. And you see the result of that is that between the outer shell and the adhesive that joins the lower shell is quite irregular. The clumps here and so on, missing adhesive here. So defects are, a part of real life in composite materials for the most part. In very few exceptional cases where the cost is not of much concern, that you can control the process completely and avoid defects. So in this manufacturing sensitive design that I would describe to you, there are three essential steps. The first is to represent the internal structure of a composite when it has been produced, having manufacturing defects. And because the nature of the defects is not deterministic, you had to do statistical simulation of that. Now, the novel part of the approach that I have been taking with my students is that we want to quantify those defects. So with the statistical simulation, we have added an aspect to that will come up with the defect severity as a measure of the defect. And then our idea will be to connect that defect severity in the step 3 to performance measures. And in step 2, you'll do the virtual testing according to what you're looking for, fatigue, static loading, what have you. So this 3-step process is sort of the main thrust of the design strategy. Here's the workflow of what we would like to see in the future. I mentioned earlier the trade-off between cost and performance, which is right here. So in order to do that, we need to have manufacturing quantified. And my colleagues on the other side in the fluid mechanics are working very hard on this aspect. People like me in solid mechanics don't bother too much with that. We wait until they have finished doing their modeling. And the situation today is that that modeling does not provide a full picture of what the microstructure or internal structure of the composite will be given processing parameters. Anyway, so this is left for the future. What I'm doing, and similar work in the literature in failure analysis, is to take that manufactured composite, characterize its internal material state, and I have called that RIMS, which is real initial material state. And as loading progresses, the initial goes to current, so the material state evolves. And that evolution depends on the defect structure in the microstructure. So there's a stationary part of the RIMS that does not evolve, obviously, such as fibers and matrix, but defects become cracks and they evolve and they affect the performance. So that enters in a physical modeling exercise where other information of geometry, boundary conditions, loading comes as well. All that leaves out as an output performance measures. And that could be for structural integrity, durability, damage tolerance, and taking those quantified measures and then the manufacturing process parameters, one would be able to, sometime in the future, hopefully, do this cost performance trade-off. So that's the idea. So I'll do two examples, as I said earlier, that are very familiar to sort of illustrate the basic concepts, the approach, and so on. One example is that of transverse cracking, which actually is should I say, in design, the target, because that's the first mechanism in most cases that occurs. And you would want to, in many cases, just be sure that it does not happen. So transverse cracking has been a lot of focus of a lot of studies. These images here show you that when you look at any instant in a cross-section of a UD composite, you see a fiber debonded from matrix, you see a crack in the matrix, and it may be that the debonding occurred first and proceeded as a matrix crack and joined the next debond, or that in a resin-rich pocket, a crack formed in the matrix, went to the fiber surface, debonded it, and proceeded that way. So those are the issues one can resolve through failure analysis. Here's another example which I showed earlier, where defect is playing a major role. So voids is one type of a defect, and non-uniform distribution of fibers, that is to say clustered fibers and resin-rich pockets, those are sort of the features of the internal structure that in this case are important. Here are certain images that show you that this early stage that I pointed to develops into a full crack, and the evidence of that comes when you increase the loading, in this case horizontal. You see the thickening of that dark area, which suggests that on one side, the composite is separating from the other. So sort of a crack has formed here. So this is a failure mode we like to analyze. So this step one of the three-step process is then to construct the RVE. And as I said earlier, this is not the RVE that is sort of taught in maybe courses in universities. The original idea of the RVE, which came from work by Hill primarily, was to see how for a heterogeneous body, you can do averages of the internal heterogeneous structure. That is a very benign type of RVE, so to speak, relatively easy to construct. But if you want to do failure analysis, where the internal structure should be representative of what manufacturing produced, then the RVE has to account for certain features of the internal structure which are important to producing the damage. And those defects that I talked about, non-uniform distribution of fibers leading to clusters, resin-rich pockets, they had to be in the RVE from the perspective of here causing failure. So I'll illustrate to you how that is done. The manufacturing defects, as I said before, in the RVE had to be put in a statistical way. So the RVE has to be sort of generated through some statistical procedures, which I will describe soon. So these are the two defects that I mentioned, the non-uniformity that had to be captured. So the main thing is, from the point of view of proceeding further, is to how much of the internal structure we should include in the RVE so it's representative. So that is the question that is called, what's the minimum volume of RVE? So I'll discuss that. So here's an example of, say, you're looking at a cross-section of a UD composite. A bigger picture here shows that there's, a lot of non-uniformity. You do a close-up and you see those aspects that I'm talking about, clustering of fibers and resin-rich pockets. So how do we quantify that? It has turned out that some work Ripley did back in 1977 is very useful here. He produced a so-called K function, because he called it K. Formula is here, and I'll talk about that in the next slide. But essentially, what is to be done is to take a certain representative area A, field of view, in which you go to the non-uniform distribution of fibers and construct this K function. So let me show what that is. So here's that picture again, and so you go to any arbitrary fiber, draw circles of radius r, and plot that radius r value here, and the K function then does a statistic of the neighborhood of that particular fiber. That is, where are the other fibers related to this one here? So what that does is to produce a KR curve that is characteristic of a certain pattern. So it's like a pattern recognition idea. If I give you one distribution of fibers, which is non-uniform, and another one that is non-uniform, these K curves will be able to show differences between those. So if it's a uniform distribution, the K will have a very different appearance. That's not enough for quantification. So a G function has been proposed. What that does is essentially from here to derive the variation, that is how the interfiber distance is changing. And that when you plot that against the R, what you find is that for small values of R, that's in the close neighborhood of fiber, you have a lot of undulations. And as you go further and further, it stabilizes. What that says is that if you are doing this statistic up to a certain point like this, 40, 45 microns, you have captured the irregularities. If you go beyond that, you're adding information that is not really doing any more useful thing. And you want to have minimum size so that in computation, you don't waste too much in doing analysis. So how do we go about quantifying this now? So that's where our novelty comes in. We have taken two different paths, and I'll describe both to you. I'm calling that as RVE construction type 1 and type 2. In type 1, which is more common in the literature, is you start out with a square window in which you place fibers in a uniform pattern with separation between surfaces constant x, that's shown there. And then you shake it. It's called shaking method. And it's, when you say shake it, you have to provide a certain algorithm for shaking. And that algorithm, then you can sort of embed your quantification. Now, what has been done in the literature is to just shake it so that it becomes non-uniform, but not worry about the degree of non-uniformity. That's where we have done our contribution. So what we do is to look at the maximum distance a fiber can travel or move when you shake it. And if you allow it to move that maximum distance and create through random generation of numbers is new positions, then the final product that you get here has the maximum non-uniformity. So we call it 100%. And then we reduce the size of the circle in which you can have the centroid of the fiber take different random positions, and proportionately then you say it's not 100%, but 50% or 30%. Let me show you examples. Of course, it depends on the fiber volume fraction. That is what's the initial distribution that you start out with. So let's say you start with 40% fiber volume fraction. With 100% non-uniformity, you look at a pattern like this. As you reduce the non-uniformity, it becomes more and more uniform. Obviously, at zero non-uniformity, you recover the uniform distribution. If there is more space between fibers, so it's 30% fiber volume fraction, you have much more irregular pattern at 100% non-uniformity and so on. Okay, the other type is where I want to see what happens to the fibers that are initially in some, say, fiber bundle in a fixed position. And as you infuse the resin, how would they create a final pattern with non-uniformity? So here what we do is we go to the central fiber, make reference there, and then go radially out and consider all the rings around it. So you're looking at the first ring here around it, and use polar coordinates r and theta, and give the fibers mobility in the radial direction as well as in the theta direction. And those are the two the variables put together provide the mobility that you give to this bundle. And if you give increasing mobility, it of course will spread out more and have less clusters. So the algorithm, which is described in the paper there, what it does is to spread out the fibers from the outer regions. So as you proceed and keep doing that until you come to a point where the distance from the central fiber to its neighbor is a certain minimum prescribed distance, because you want to have some resin there to put finite elements in there, minimum 2. So this is the pattern that you generate when you specify those mobility quantities, dr and d theta. Here's an example of a low fiber mobility, and you see it's very clustered. With a high fiber mobility, it's less clustered and begins to have resin rich pockets. So that's sort of the idea. Now, getting the minimum RVE is the next step before you do failure analysis. And the idea that I actually described earlier is to get a certain statistic to calm down so that if you increase the size of the window, it does not add any further useful information. So here in this particular shaking method, there's a statistic. I don't have time to describe that, but the concept is clear that that statistic changes, varies until you come to a certain point beyond which it's not changing. So that 200 fibers in the window would be the minimum size that you need to use. And that's the size of the window. You put additional fibers around it to protect that window from edge effects. So you're applying the uniform displacement to this RVE. The edge effects will be in this region. You go away from it and do your failure analysis in this region here. The other type where the final pattern is not rectangular. So what is done is to encircle it with a circle and then embed that. That is called a cell. Embed the cell in an outer region. Now, why? Is because this is not totally suited for applying boundary conditions. So it's done commonly in the literature, not so commonly, but this idea is out there that you do embedded cell. So outer region is a homogenized composite. It's a straight boundaries. It's in this case, a square region. And then we use the hill idea. The hill idea is that if I apply to the boundary uniform displacement and I get uniform traction resulting from it, then I'm fine. So if I reduce the size of this outer region, you see though this is the reduced size, it gives a non-uniform result. That is, if I apply uniform displacement, I get non-uniform traction. I keep increasing the size until I get to this equality of uniformity in both cases. So those are details you can find in papers if you wish. Now the failure analysis, I need to spend maybe a minute to explain my philosophy. Failure analysis is legacy of what we have been doing for metals and so on, where uniform conditions often exist. That's not the case here. And using stress analysis causes, in my mind, difficulty because stress is a tensor and you cannot separate it so easily. So why? Let me explain that. So here's a non-uniform pattern. I'm applying remote stress sigma. If I go to a point like this, which is the polar point or close to the polar point, there's intersection of the axis of loading to on the fiber, then typically I have dilatational or close to dilatational stress state. What that means is that all three principal stresses are tensile and equal or nearly equal. That is, you will have only volume expansion here. If you go to a point like this here, then you get mixed stress state. That is, say, this is distortional. It has both shape change as well as volume change. With energy, you can separate those two quite easily because energy is a scalar quantity. So if I look at the total strain energy, it's split into dilatational part and distortional part. The dilatational part here will become critical when the volume expansion takes a certain value. What that means is that volume has expanded. At a certain point, the material cannot bear any further expansion and it bursts as a cavity or forms a cavity that bursts open. So we discovered this mechanism back in 1996. I'll talk about that in the next slide. Most people really look at only this situation of distortion energy and then describe it with von Mises stress criterion. I'm a firm believer of that strategy leading to problems of fundamental nature. Okay, so here back to this particular point. Here's what happens. The cavity forms here. And we devised back in 1996 a method called poker chip method, which was actually taken from some research in rubber by Ghent. Anyway, what the important point to mention here is that there's a method to independently assess and find the critical value of dilatational energy density, which will cause this cavity. And this cavity is surrounded by a brittle region because there's no shear, and therefore it expands like a should I say, burst opens, so to speak. The value of the dilatation energy density formula is here, and the value comes out to be for epoxy very small, 0.2 megapascal. What this means is there's no other mechanism is able to compete with this particular mechanism. It's an energy dissipating mechanism, failure mechanism, and there's no other mechanism of crack formation that comes close to that. So this is sort of the first mechanism if its conditions are right. That is, it has dilatation energy density. Now, this is going to take time to describe, so I'll refer you to the paper. So what we do essentially is to look for the right conditions, three principal stresses being equal. We plot the ratios of it, and at applied strain of approximately 0.3%, the three principal stresses become nearly equal. And then we look at how with the applied strain, the maximum dilatation energy and distortion energy values are changing. And we find that before you get to this point, you have already satisfied the minimum criterion. That's a criterion for minimum energy density for dilatation. So that happens in transverse crack formation. Here's the final result, which I think is quite logical and understandable. What is done is to do this procedure of statistical RV formation virtual testing, and then do a number of virtual tests like you do in a laboratory and get a scatter. So these points are scatter points of virtual tests. And what is being plotted is that the mechanical strain that you apply to the virtual specimen and find the first point of the loading that you have brittle cavitation occurring. So that value, what you see is that just over 0.3% in this case, it is a 60% volume fraction, which means there are larger clusters. As you reduce the volume fraction, clustering reduces, and therefore you have to do more work, or should I say less probability of finding a place where dilatation energy density becomes critical. Anyway, as you increase the non-uniformity, and this is sort of the new result, so you are quantifying now this effect. So if you're a design engineer and you want to assess that your product has much less control and therefore higher level of non-uniformity, you will go to this value. If you think that is very well controlled with uniform distribution of fibers, then you go to this value. Okay, this is a result which is also of interest. It's approximate because it should have been 3D, but it's 2D. But anyway, I think it qualitatively explains a certain feature that is not intuitively obvious. If I use glass fibers in epoxy versus carbon fibers in epoxy, for the same clusters of fibers, the initiation of dilatation induced cavitation is earlier in carbon because of the high stiffness mismatch. Now, carbon fiber is believed to be good in every sense, but that is really not the case here. So that's something also to point out. Here's another result which sort of presents the same overall result in a different way, where the clustering of the fibers is here rather than non-uniformity measure. Now it's a clustering of fiber measure. So more clusters you have, lower will be the applied strain at which you will cause cavitation. We also done analysis what happens to crack formation from cavitation point. Of course, it requires higher strain. So this is an initiation, and that's the progression to crack formation. And you can see that with dispersed fibers, the higher value is needed to cause cracking, while clustered fibers would do that earlier. So hopefully these are good design guidelines for people concerned with manufacturing. Okay, I'm going to shift gear and go to another example, which is very different, but illustrates the concepts of this particular strategy. So we are looking at unidirectional composite under axial compression. And at some point, what happens is that you form a kink band. This is now a classical result. Everybody knows about it. This is what happens. At some point, the fibers break along a certain in a certain direction or along a plane, and another set of fibers fail in a parallel plane. So between that two is what you say a kink band has formed, because it's a kink here. And between those two planes, the fibers then undergo rotation. So in Budiansky model, which is classical for this, geometry constructed has parameters of initial fiber misalignment phi, the rotation of the fibers within the kink band, phi sub s, and this is the bandwidth, and beta is the tilting angle of the kink band. Okay, using all that with a refined analysis, Budiansky produced this relationship that says what is the stress that you apply at which you have rotation of the fibers. So it's an academic result, very exciting and all that. But you ask yourself, if you are designing and you don't have kink band to look at, you don't want to have kink band, how do you get this sort of information in your design? So you had to do some estimates. Well, it turns out that in 1983, the Budiansky model that came was actually generalization of something that Argonne, in a very intuitive manner, produced earlier in 1972. What he said was, if I have one fiber in a uniform parallel fiber set misaligned with this angle phi, what would it do, or what would it take to have this misaligned fiber trigger something that will lead to kink band? And it's a remarkable way of thinking about it, because that's the only information you can reasonably have when you have manufactured a product. So his formula is really, you would say, specialization of this formula. We will put beta equal to 0 because the kink band has not formed yet. Put phi s equal to 0 because the fibers are not rotated yet. And then you get this result that 10 years earlier, Argonne produced in a much simpler way. And I'll show you that this result is very useful in doing this type of analysis of failure that I'm talking about. So let's go to that. So this is work that has been done recently by, interesting thing is that when you have students and they become professors and they have students, and you can visit them anytime you want. So I went to one of my former students who was a professor in Chalmers, and they told me what they were doing. And I'll describe that work to you. So what they were doing is supported by Volvo. They were producing thicker unidirectional composites using bundles, non-crimp bundles rather, and then looking at, with certain image analysis that they developed, looking at how much was the misalignment. And they were plotting the misalignment here, angle, with its frequency. So, and then we're fitting Gaussian curves to that, going to very high level of probability, 95% or so, and picking up that angle. And that's the maximum misalignment angle they were using in Argonne's formula and finding excellent correspondence with the data, failure, compression data, failure data. Using Budiansky, with estimating fiber rotation and all that, you were getting conservative results. But this was fit very well. For different badges, here are the correspondence, which is sort of tells you that the Argonne formula worked quite well. So I came into the picture and made the following observation. Argonne, of course, was trying to develop very simple results by using a single fiber misalignment. In reality, you don't have that. You have clusters of fibers misaligned. It's a misalignment in coordination, so to speak. So you have images like this here. This is just a sketch. Is that a bunch of fibers next to each other become wavy and therefore misaligned. So inspired by some fraction mechanics analysis, I said, let's smear these together as ellipses, like you could say, area of influence of this, and then put those ellipses in a solid and consider these to be sort of elliptical cracks. Of course, they are not cracks, but you use a similar idea as if these were cracks. So I constructed a measure of defect severity with three parameters in it. Two are the, should I say, smeared out ellipse characteristic values, area of the ellipse, the minor axis length and orientation of the ellipse, and then the misalignment angle maximum within the ellipse. Okay, so this defect severity measure that was constructed actually worked out quite well. So details are in the picture, in the references you can read on your own, hopefully. So essentially, this is what was done. You take represented two images of the manufactured product, produce computer generated images of that with fiber misalignment, turn them into elliptical regions, go into the finite element model, and then apply the failure analysis based on Argonne and some a little bit more. And then you find which of the elliptical regions will be the first one to cause compressive failure. And the correspondence was pretty good with the experimental data. Okay, so with this, I want to save some time for Q&A and essentially summarize what I have presented today. First point is that manufacturing defects are a reality. Aerospace industry is still operating on something like arbitrary 2% volume fraction of voids. If you are less than that, you are okay. I think it's not going to cut it. We have to live with defects. If you try to minimize defects, you can increase the cost, and you don't know when to get to the optimal. So that is the reality. The stress and failure analysis must incorporate defects appropriately, not like what we were doing back 2 decades ago, putting artificial defects and doing testing. Testing is limited physically, so we need to do virtual tests. The novelty of this approach I described to you is that I believe in quantification. So the defect severity is quantified, damage mechanics is there in a very quantitative manner. Merge those two together to create a certain strategy for failure analysis. And that is the manufacturing sensitive design. Now, in future, what I see happening is that we will put all these algorithms that I described and physical knowledge into a machine learning process with artificial intelligence. So that's, I'm approaching my retirement. I don't know if I will be able to do that, but hopefully that will be the future direction for the work. I put the references of recent publications connected with this. You may want to look at those if you wish. much for your attention. Fell asleep and went away. Ready for any questions. Thank you.
My name is Jonathan Goodsell, and we want to thank Professor Talreja for his excellent presentation, and I'll be fielding the questions. As a reminder, please put your questions in the Q&A box, and we will ask those here to Professor Talreja. We have about 10 minutes for the questions and answers. And so we'll begin. One of the first questions we received, Professor Talreja, was about the case of random excitations. And in the case of random excitation, how would one estimate the onset and propagation of cracks and failure?
Okay, now I did not quite discuss random excitation. What I discussed was a virtual test where you apply a uniform loading, which is not random excitation, but you could say constant amplitude type of excitation. Back in my PhD work in 1974, I think, I did work on random excitation. So there are ways to connect the quantitative measures of random excitation to the consequence of that. But that part is just characterizing the loading as a random, not the failure as another random. Failure has its own randomness, and that's what I treated in my presentation today. The next step will be to connect quantifying the randomness of the failure to the random applied loading. So I would not recommend using minor type of rules, but there are much better procedures for characterizing random excitation for, say, in the case of wind energy, the wind loading is quite random. I hope that answers the question.
Thank you. Another question here about, with a number of questions all around the RVE approach, and we'll try to lump some of those together. But the first question is a basic question about getting the properties of materials, and of course needing the properties of the constituents in the microstructure. This person asked the question, I know of the method to use a data sheet or to find all of the mechanical properties of both fiber and matrix, or use a data sheet for some and use testing for other properties. Do you have a strategy in your experience that has proven effective for determining those constituent properties?
Well, I'm a total believer of material properties as defined in the classical way. That is, a material property is a property independent of the geometry of the specimen, independent of the loading mode. So a material has a certain characteristic behavior that is captured in certain constants called material properties, like Young's modulus, Poisson's ratio. Now, in this approach that I described, in addition to those material properties, we need failure-related material properties. And I'm very adamant about that. I think what's happening in the literature, unfortunately, is using fancier models like cohesive zone model, where you have material parameters appearing that there's no way to find them independently. The particular approach that I described, the material properties are dilatational energy density at cavitation formation. And that can be found by an independent test. Those tests that particular type of test is not standard yet. And it's not easy to do, but that's the way to go. So I know in the industry, you use those sheets of manufacturing a company giving you data. No, that's not good enough for failure analysis.
Thank you. And following on that line of data and so on, someone raised the question of how could the machine learning approach potentially be applied in this general field of manufacturing and defect simulation? Can you comment on that?
Interesting question. It's something that I'm working on right now. There are two parts to that. Machine learning can be, in principle, can be used to characterize how a given manufacturing process is progressing so that you can intervene and change it to produce less defects. Okay, we are not that far yet. We are still struggling with physical modeling of manufacturing process. What is happening today in machine learning is that at some point when you say, I'm not getting anywhere with my physical modeling, then you take a computer and allow the computer to help you out. And that particular approach is called supervised machine learning. If you cannot do that, then you do unsupervised machine learning. I would say let's not jump to unsupervised yet. Let's do the supervised first. But we have not done that yet. There are only very few papers in the literature on machine learning related to manufacturing process. Now, coming to machine learning that I talked about here in my concluding slide is something that I'm proposing will happen where we do all this RVE algorithms and so on with respect to physical phenomena in a way that we can improve that process by having computer do it for us. That is, we teach the computer, machine learning, there are several processes there that are really simple, but they are tedious that we humans are not willing to do. But all this is still in infancy. So I cannot give you a specific answer as to how to do that, other than to say that that's the direction in which we should be going.
Let me take this in another approach. Someone raised the question that much of the industry is starting to show interest in thermoplastic matrix composites as opposed to thermoset matrix composites. Though thermosets are certainly still very, very active. And the question was along the lines of how much of this, what parts, and so on, commenting on the applicability of these methods over into thermoplastic-based materials.
Yeah, very fair question. I did not include that discussion in the presentation because the data is not as much. But most of what we have collected over the decades is with epoxy. So, this dilatation energy density value that I talked about is for epoxy. Thermoplastics are fantastic. I think there's amazing things going on in manufacturing with thermoplastics. But we'll have to go slow, not just take what we have from epoxy and say with thermoplastic, all we do is add some inelastic deformation to that. No, because the nature of the bond between fibers and thermoplastic is not the same as between, say, glass or carbon fibers and epoxy. So what I described cannot be directly used in terms of quantitative numbers, like the strain to formation of a transverse crack. But we'll have to do work in that direction using thermoplastic, gain some data on which we try out these modeling ideas.
Very good. We have a question now going back to one of your early slides where you discussed process modeling and maybe fluid mechanics type modeling feeding into the damage modeling and solid mechanics. And this is a question from perhaps a process modeler who asks, what can process modelers do to support damage modeling? Are there particular parameters coming out of the process modeling community that if developed or focused on would provide particular utility in the failure, damage, performance prediction world?
Yeah, excellent question. This is where we had to work together. So, for instance, if I tell you that I'm interested in transverse crack formation, and I'm doing this, should I say, artificial RVE generation, because I don't know what manufacturing actually would produce. So if you are on the side of manufacturing process modeler, you need to try to tell me what are the end product internal characteristics that you can expect. So if you take certain processing parameters, say distribution of pressure, temperature, and all that, and you say with those numbers, you're going to get fiber distributions that are like these, then I can use those in my RVE construction rather than do some artificial things that I described. Because, at this point, I just want to understand how irregularities of fiber distribution affect formation of a transverse crack. So I do, some quantitative way to systematically see those effects. But this is in vacuum. That is, I don't know how, if I change the manufacturing parameters, how the initial conditions will change. So that's where my process modeler colleagues will have to, join hands with us.
Thank you. I think we have time for one more question. And as a number of questions involve RVE, and you made that point very, very well, that this selection of RVE is a little bit different than perhaps the traditional homogenization, dehomogenization RVE. One of the participants asked you to comment, if you would, on again on the difference between RVE for non-damaged situations and RVEs for damaged situations, and provide any guidelines to practitioners, rules of thumb, so on, to clarify or make sure that they're doing the RVE process for damage correctly.
Yeah, but that is really my hope, So, for instance, let me see if I can go to a slide to illustrate this very quickly. No, it's not there. One of the final results. Yeah. So let's say that I'm looking at the top curve at 0.53% failure. That will be for uniform fiber distribution, right? So as I increase the non-uniformity, that particular design value of failure initiation falls. So this is the type of guidance you need. So you make an assessment. You say to yourself, okay, given a certain volume fraction of fibers, I have a well-controlled process. It is as good as uniform fiber distribution. Then I take that value, 0.5 some percent. But if it's going to be non-uniform, then I actually gain something. But this gain is from the point of view of initiating debonding, or more correctly, initiating cavitation. But if you have other damage mechanism, you're not applying transverse tension, but you're applying transverse compression, the picture will change. And I don't have time to go in all five. There are 5 basic modes of damage or failure for unidirectional composites. So one has to make, as a good designer, one has to see, which is my main loading mode, and therefore main failure mode, and then take these type of results as guidelines.
The webinar is recorded and will be available on the website. If you already have email address with us, we will send the link to you. With this, and we will close this webinar, and thank you all for participating. Thank you.